integral representation of Euler sum for r equals to 1. So basically over here I have a generalized Euler sum, yeah, represented by s p to the order r comma q, and this sum is over here. And you might have known that as k is just the harmonic number, and if given the order of p, we write as k to the order of p as the following sum from n equals to 1 to k of 1 by n to the power p. Yes, others like it's quite easy to understand this all. Yeah. Now let us try to find the integral representation for a special case when r is 1, that is for s of p comma q, and the sum is basically sum from k equals to 1 to infinity as k to the order of p by k to the power q. Yes. Now for this sum, first of all we can just try to find the integral representation for as k to the order p, and then divide by k to the power q and take sum. But first of all let's try to find for this only. And again, to find integral representation for this, we first need to have the understanding of how as k is represented as sum and integral. We know that the integral representation for this is integral from 0 to 1, 1 minus x to the power k by 1 minus x dx. Yeah. Similarly, in the sum representation, it is sum from n equals to 1 to infinity 1 by n minus 1 by n plus k. Yeah. Now these two sum and integral are equal, and if we differentiate, if we go on differentiating these two, in the sum over here we will basically have this as k of some order, and over here integral, and basically those two will be equal, and that's how we can find the integral for the sum of the like harmonic sum of some order. So if we go on differentiating, in over here, yeah, we know that this two are equal. If we basically take the pth derivative, okay, let's try to take the first derivative over here, and that will just be sum from n equals to 1 to infinity of 1 by n plus k whole square, and that over here is integral from 0 to 1 minus x to the power k. Basically I'm differentiating with respect to k. Please note that our differentiation is with respect to k. Yes, minus x to the power k times ln of x by 1 minus x dx. Yes. Similarly, if I differentiate one more time, here we will have minus 2 factorial sum from n equals to 1 to infinity 1 by n plus k to the power 3. This is integral from 0 to 1, again minus x to the power k times ln of x whole square, because we are differentiating with respect to k, by 1 minus x dx. If I go on differentiating, whenever there is a minus p factorial over here, there will be p plus 1. So basically if there is minus p minus 1 factorial, yeah, and okay, also regarding minus sign, in the next differentiation we will basically have again minus 3 over here, so just 3 factorial, minus 4 factorial, then 5 factorial. So basically if we have odd number here over here, here's a minus sign, so that means we'll basically have in let's say in pth differentiation, we will basically in p minus 1 differentiation we will basically have minus 1 to the power p minus 1 factorial sum from n equals to 1 to infinity 1 by n plus k to the power p. This is equal to integral from 0 to 1, and then minus of x to the power k times ln of x to the power p minus 1 by 1 minus x, 1 minus x, and then dx over here. Yeah, dx. Okay, now next we know that this sum over here, this is just, you know that sum is basically this is going from k plus 1 to the power p up to infinity. Yeah, So you can say this as Riemann zeta of p minus h of k up to k to the power p. We can write it like this, isn't it? Basically, this sum is going from k plus 1 to the power p to k plus 2 to the power p, k plus 3 to the power p infinity. Yeah. Basically, from Riemann zeta of p, yes, yeah. So it goes from 1 to infinity. That means the Riemann zeta of p minus from 1 to k is subtracted. So as k of p. Yeah, that's correct. And now over here, it's integral from 0 to 1 minus x to the power k ln of x to the power p minus 1 by 1 minus x dx. Yes, dx. So what would be our next task? So basically, since we want to separate h k to the power p, we can take this minus sign and multiply it over here so that the order of them is changed, and after that take this to other side and divide it. Yeah, so we get h k to the order of p minus Riemann zeta of p is basically minus 1 to the power p by minus 1 to the power p by p minus 1 factorial, and then integral from 0 to 1 x to the power k ln of x to the power p minus 1 by 1 minus x dx. Yes. Okay, now let's take zeta of p to other side. That gives us hk to the power p is basically Riemann zeta of p plus minus 1 to the power p by p minus 1 factorial, and then integral from 0 to 1 x to the power k by ln of x to the power p minus 1 by 1 minus x dx. Now this is basically the integral representation for kth harmonic number of order p, but this is not the answer that we are seeking for. You also have to divide this by k to the power q and then again sum it. So sk to the power p by k to the power q is equals to Riemann zeta of p, divide this by k to the power q plus minus 1 to the power p by p minus 1 factorial dividing by k to the power q. Yeah, integral from 0 to 1 x to the power k. Yes, and then we have ln of x to the power p minus 1 by 1 minus x dx. Okay, now let us sum this whole thing from k equals to 1 to infinity. Let us do that. If we do that over here, we will just have the same expression, sum from k equals to 1 to infinity of sk of order p by k to the power q. Now this is the required sum. Over here, Riemann zeta of p will just be a constant in this sum, and summing from k equals to 1 to infinity of 1 by k to the power q, that is just Riemann zeta of q. And then plus over here, since this is a constant, we can take this inside the sum. And over here we have x to the power k by k to the power q, and these are the only terms involving k. Yeah, and we know that x to the power k by k to the power q when summed from k equals to 1 to infinity, that is just liq of x, polylogarithm function to the base q of x. Yes, so we have integral from 0 to 1 liq x ln of x to the power p minus 1 by 1 minus x dx. So finally we have our required integral representation, and this integral representation will be helpful. Let's say if we have to find sum from k equals to 1 to infinity of hk to the order 2 by kq. If you have to find this sum, let's say, you can use this representation and find the answer. Though you will have to do some work to solve the integral over here, but that will not be undoable. That will be kind of easy to do and simple, which you can easily do. We'll also solve this problem in upcoming video. Yeah, we will do this using the same integral representation. Just give a try, and if you want to, you can keep watching my next video to learn about it. So thanks for watching, and to talk about the flow of the problem, flow of the solution, we just first used the integral and sum representation for s of k, that is kth harmonic number, and differentiating the both sides, we eventually got the integral representation for kth harmonic number of order p, and then dividing by k to the power q and summing up, we got our required result. So that was it. Hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the upcoming videos too.